Welcome, everyone. Thank you very much for coming. My name is Julian Milthorpe. I am the Secretary of AusYGN, as some of you may know. I'm here today to welcome Pablo Luna to give us a presentation on his work at the Embalse nuclear reactor in Argentina. I met Pablo at the IYNC 2018, where I got to see a similar talk, and I just thought it was amazing, the sheer scale of the work, the complexity, and the size of the job in the refurbishment of the steam generator head. I thought it was so important to share this with you guys because I knew it would bring a lot of value to us at ANSTO and at AusYGN and globally to our professional networks. So Pablo is a highly experienced engineer. He graduated in materials engineering, specializing in the technological applications of nuclear energy. Having worked for NASA for 16 years, he'd been involved in a large body of work, including maintenance and performance evaluations of steam generators and life extension assessments for nuclear power plant systems, structures, and components. He was in charge of feasibility studies for the replacement of steam generator components and has recently been involved in the final part of the installation phase for the new Embalse steam generator head, which he'll talk about today. His talk will detail the complex engineering design challenges tackled over the course of this significant project. So, without further ado, I'd like to thank everyone again for attending, and could you please show a round of applause for Pablo.
Hello, everyone. How are you? Before to start, I would like to mention a couple of things. First one, thank you very much, Julian, for inviting me to share this experience with this important audience, the young generation in nuclear in Australia and the Australian Nuclear Organization. Thank you very much. Second thing, I would like to congratulate you for the beautiful country you have. I had the chance when I was younger to spend almost a year in Australia, and I always dream in coming back someday to have a good beer at the Rocks, you know. So, so thank you very much, Julian. So now I think I can start sharing the presentation. Yeah. Give me a second, please. Okay. Can you see it? Can you see the presentation there?
Yes, we can see that, Pablo.
Okay, great. One thing about this presentation is the first time that I have to put two dates in the presentation. So I will be basically presenting to the future, you know. So something funny to break the ice. I just want to say that even this it was a project of a specific mechanical implementation. Some of the messages I want to leave to you at the end are applicable to all kind of project of any engineering field. So let's start. Let me make a small introduction to our company, Nucleoeléctrica Argentina. Is a state-owned company, and we own and operate 3 nuclear power plants. Two of them are a PHWR vessel type from Siemens design, Atucha 1 and Atucha 2. Atucha 1 was connected to the GERD the first time in 1974, and Atucha 2 was connected to the GERD in 2014. And then the Embalse nuclear power plant is a CANDU 6 PHWR reactor with pressure tubes, and was connected the first time to the GERD in 1983, and reconnected to the GERD after the refurbishment a few days ago, after the entire refurbishment we did at the plant. The project I want to present today is about the replacement of the steam generators, but this was only a part of a bigger project, which was the refurbishment of the plant as a part of a plant life extension project. Embalse was reached the design life at the end of 2015, and then the refurbishment outage started in order to reach another life cycle. This project started back in 2006 with the analysis of all the structures and components, and the definition of the scope of all the modifications and replacements that we have to implement based on the aging assessments of the plant. Then we got a stage of once we was defined the scope, we reach a stage of preparing the components, manufacturing of new components, preparation of all the technical specifications, and then the implementation phase started in January 2016, in which we really start all the work at site. To understand the entire scope of this project, during the refurbishment, we have the main activities was the fuel channel replacement, basically the replacement of the core of the reactor, the steam generator replacement, the moderator system component replacement, heat exchangers and bulbs, some improvements of mechanical, electrical, and instrumentation systems, and the operating of the reactor, the turbo generator, and the entire balance of the plant. So it was a quite big project. Part of it is the project that I want to present today to all of you. Okay. This is what we have in the nuclear power plant in Embalse. This is you can see on the left side of the slide, you can see the primary heat transport system with the main components. We have 4 steam generators, 1 pressurizer, 4 main heat transport pumps. We have down below the Calandria vessel that contains all the fuel channels, 380 fuel channels, which basically contains the fuel bundles. And the reactor is connected to the pumps and steam generator with we call it feeder pipes. These are carbon steel, 2 inches to 3 inches diameter pipes. You can see it in the slide with all the green spaghetti you can see there. Well, these are all the feeder pipes. So it's a quite different reactor what you may be used to see in PWRs. On the right side of the slide, you can see the type of steam generators we have. We have 4 of them. These are vertical recirculating steam generators with the Incolloid 800 heat exchanger tubes. And the original steam generators had internals of carbon steel, tube support plates made of carbon steel. On the lower part, you can see here, the lower part is the riser, is where all the light water boils, okay? And here, the upper side, the upper part is where all the mix of water and steam is separated, and so we can get dry steam at the top. And through the inside of the tubes, it circulates the heavy water from the primary heat transport systems that transfers the heat to the light water side in order to produce steam that then goes to the turbine. These components are located in a bio wall. It's a shielding wall, concrete wall, and they're supported by a column down below here, a column of 15 meters high. Okay, this is in order for you to understand the type of components and reactor we have here at Embalse. Now, during the years of operations, during the maintenance outages, we identified that the carbon steel internals suffered some kind of degradation. Mainly, we identified at the top the primary cyclone separators. We identified erosion of the carbon steel cyclones. And down below, and even more important, we identified the tube support plates, this one here, the ones that support in a lateral direction all the tube bundle. We also found erosion of the carbon steel plates. You can see it here in these 3 pictures. And on the hot leg of the tube bundle, where the hot heavy water enters, we found blockage, sludge blockage of the water. So basically what happened is that this blockage redirected the flow through the cold leg side, increased the velocity of the flow, and then produce erosion to the tube support plates. Basically, it was a combination of susceptible material, carbon steel, lack of access for inspection and maintenance. We didn't have any access to see what was happening, and a high transport of iron. And with this degradation in course with the components, it was really important to define whether this component can be operated for 30 more years or not. In case that they are not feasible for the new life cycle, then the entire life extension of the plant was in risk. At that point, the 6 plant was not feasible to do a life extension if you have to replace these large components. Okay, so we basically, after discovering this issue, we enter in a decision-making process to decide what we should do with the steam generators and with the entire plant. This decision-making progress I want to show you here because it was a logical process of different options that we had. First of all, as I mentioned, we evaluate with the life assessment. We evaluated really the possibility to replace these support plates or not, and basically the conclusion was that they have to be replaced in order to be feasible to operate these components for another life cycle. So in that scenario, we start to evaluate what is the best methodology. So we have two options: was the replacement of the internals, of the entire internals of the steam generator, or the replacement of the entire component. We evaluated this with the support from the designers, the plant designer and the steam generator designer, and we got the conclusion that there was not feasible to replace the internals. So we needed to face a replacement of the entire component. Again, the next step was to evaluate the best extraction route. You know, most of the steam generators are replaced through a temporary hole in the containment building. We evaluate this option against the option of the equipment airlock. And because of the configuration of the containment building, was concluded that it's not possible to perform a temporary opening in the building. So we had no option that replacing components through the equipment airlock. It was made by the technical assessment with the support of the designer and ourselves. And then if we have to replace the component through the equipment airlock, we face two options. We needed to understand if a complete component replacement was feasible, or only the part that present the worst degradation should be replaced to that point. And basically, with the interferences analysis, we conclude that the only option to replace our components was the replacement of the lower part, where the tube support plates are, and refurbished the top or the upper part of the steam generators. And that is how we define the option of this kind of replacement. But when you see the configuration of the Embalse plant, you start to understand the complexity of this work. All you can see here is the reactor building, okay? And then you have here in red, you can see the 4 steam generators, okay? And here, down here, with this side, you can see the only extraction route feasible. So the steam generators are in a different levels and different rooms of the distance from the extraction route. So the temporary opening in the building was not feasible. There is no lifting facility like in all other PWR plants, we don't have here a big polar or overhead crane to handle these kind of components. We have only a small bridge crane at this elevation, okay, only to handle the pumps, but they don't have enough capacity, and they are in a lower level than the steam generators. And the equipment airlock it has a clearance smaller than the upper part of the steam generator. So this is how we get this kind of a scope. And definitely these kind of plants were not designed taking into account the replacement of big nuclear components. So when I got this point, you know, I had the same feeling when I was a kid, you know, and I saw, I was about 32 years old when I got this point in the project, and I had the same feeling when I was a kid, you know, and I saw for the first time a ship into a bottle, you know. So how can this be done? The problem is that when you're a kid, you have your parents, you know, or someone to ask, and they tell to you how they do that. Now with this project and most of the first of the kind nuclear projects, you don't have someone to ask how to do it. You have to develop it. So that's what we started to do, to research and develop. So the first stage after the definition of this scope was to do a feasibility study. Okay, we have this option. Is doable? Can we do this? Okay. We need to evaluate it. So basically what we did, we started to do two modelings in parallel. One modeling was made by laser scanning. So we did the entire modeling of the reactor building with laser scanning, a cloud of points. And with all the drawings, design drawing, we started to model also the structures and components, and start to do validation of the model. We have to validate the model we built with the measurements we were taking with the laser scanning. And this is because during this stage, the plant was in operation. So you don't have access to all these rooms you need to evaluate during operation. That is why we only had 1 month access during the planet outages, and then 1.5 years you don't have access until the next outage. So that is why it was so important to build a laser scanning model. So we could validate the drawings and this model with the measurements made by the scanner. This was the first stage. So as soon we confirmed that the clearances of the structures are okay to take these components out, then we could define the scope. And of course, we have to build the new components. And for doing that, and because of Argentina has a long history in nuclear, we decided to do with the qualification of local contractors and the right support from the designers. So we had to build new 4 steam generators in Argentina, and also supply all the heat exchangers, all the new heat exchanger tubes with a supplier here from Argentina. And then we have to face the scope for the construction work at site that involved primary steam separators replacement, we defined, because of the schedule we have, we defined to do it one by one through the main way of the components before cutting the upper part for the replacement of the lower part. So there was a handcraft work of replacement, the 312 steam separators and molded 1200 drain pipes. Then we have to cut the upper part, to handle the upper part inside the reactor building, storing, and to perform the beveling for welding the new lower part, and fitting and welding the new lower part. This involved the movement of the 4 60-ton steam drums inside the reactor building, and perform a fitting and welding of the 2.5 meter diameter steam drums to the lower assemblies. Then we have the handling of the old components and new old components out and new components in through the different rooms and levels. These are the old lower assemblies were 115 tons each, and the new one 130 tons each, with a 12 meters height and 2.5 meters in diameter. There was a big part of the scope, the handling, and then fitting to the process piping to the plant. And then, related to all this, we have to remove and reinstall all the interferences. This involved about 10,000 meters of cables, 1,700 meters of process piping and tubing, and more than 100 tons of steel and concrete structures. In total, this project involved the movement of 3,000 tons of devices, systems, and structures inside the reactor building, and more than 1.5 million man hours for the execution of it. So based on this scope, we defined the Embalse steam generator replacement became a first-of-the-kind project. And as you may know, in nuclear industry, to be the first of the kind is a big challenge, because everything needs to be developed, research and developed, and you have a lack of reference to perform the different activities. So on the right side, you can see each part, the upper part to be reused and refurbished inside the reactor building, and the lower assembly, we call it cartridge, is the part that we replaced. So how we structured this scope? Basically, it was a strategy to involve national contractors with national bid, and to involve specialized international companies for critical activity. And also we have the support from the plant designer, Kendo Energy, originally ACL from Canada, for the review of some engineering, mainly the engineering related to the new manufacturing. So our company decided that we were managing the project ourselves. So the management of the entire project was performed by NASA. Then the supply of the new components, the new steam generator cartridges, was structured in the following way. Was qualified, identified and qualified an Argentinian contractor called IMSA for the main assembly, and another Argentinian contractor for the supply of the new heat exchanger tubes. The design of the new component was performed by Babcock & Wilcox, Canada, who is the original designer of the steam generators, and also provided the new tube support plates and new 4 tube sheet assemblies, and as technical specification from the plant designer ACL or Can Do Energy. This is how we structure the supply of the new components. Then the construction at site, we also wanted to maximize the local contractor participation and involve, of course, specialized companies for the critical activities. So we identified for the rigging and handling, Mammoth company from the Netherlands, which is the specialist, with support from a local contractor, EISA, and Roman. For the cutting, fitting, welding of the new steam generator to the existing steam rams, we got support from PCI Westinghouse from US, and also support from the local contractor EISA. For the moisture separator replacement, this is the refurbishment of the upper part of the component. We involved for the engineering to the original steam generator designer, Babcock & Wilcox, Canada, and the construction site activity was performed by the local contractor EISA. And all the removal and reinstallation of interferences was performed by the local contractor. So this is how we face the new manufacturing. At that point, all the local contractors were out of nuclear business for a long time. So we had to face a new qualification process for the steam generator manufacturer and for the heat exchanger tube manufacturer. So this process involved a pre-contract stage in which we perform QA technical evaluations and familiarizations with a typical technical specification. Then we, after the contract hour, it was a stage of a formal qualification and certification of the component manufacturer with a qualified nuclear authorized inspectors, and also by obtaining a license for fabrication of the Babcock & Wilcox design. This support was provided by the original steam generator designer. And then when they have this QA certification, they could start the production process for all the components. And for some critical manufacturing processes, we required a special pre-production qualification. Basically, what we had to perform is a sample of the subcomponent to be manufactured with the same materials and same procedures to be used during production, and then submitted to us for evaluation, non-destructive evaluation and destructive evaluation at the laboratories. Once they had that sample approved, they could start with that critical process of the manufacturing. In the case of the heat exchanger tube supplier, they had to produce a lot of 150 tubes, and they qualified in the first official submission. That was a very, very important achievement, and was a great success in the preparation of the production activities. They produce over 14,000 heat exchanger tubes made of Incolloid 800. Then the steam generator main supplier was implemented in the province of Mendoza here in Argentina. And you can see some pictures here of different stages of the process. The upper picture, you can see how we assemble the primary head to the tube sheet. Then you can see a picture of the tubing of the steam generator, and the lower pictures shows clean room activities and ready for transportation. They basically manufacture with the manufacturing procedure supplied by the original designer. And based on that, this local contractor developed applicable manufacturing drawings and procedures. Here you can see the scope that was supplied by the original steam generator supplier from Canada. They supplied the new design. They also supplied the 4 new tube sheet assemblies and the stainless steel new tube support plates. You can see here, these plates are made of stainless steel and are lattice bar design. You can see here some pictures of the arrival of the 4 steam generators at site. They were delivered on August 2016. This was related mainly to the manufacturing stage. Then, in the meantime, we had to face the planning of the construction stage at site. So here, let me comment to you some specific features we have to develop and implement for this kind of replacement. We have to install inside the reactor building a temporary crane. You can see it in the picture. It's orange, you can see it. It's a knuckle boom crane, the same that is used in the ships. So we could reach any point of the building with this type of crane. Also, during the refurbishment of the top part of the steam generator, you can see them in the picture as well. Was designed to be performed one by one through the mainways. All the steam separators were replaced one by one through the mainway in order to start in advance this activity before the lower assembly replacement. Also, we have to design a cartridge transport through the airlock, to the equipment airlock, that allow for the rest of the activities of the refurbishment outage to keep going on. We couldn't block the entire equipment airlock because all the activities had that access for implementation of different scopes. Also, and very important, we have to cut the process piping, the primary heat transport process piping connected to the steam generator. We have to cut it well in advance to the replacement in order to allow a previous metrology and fitting of the new components. So for doing that, we have to implement ring type cutting. So we have enough clearance to do all metrology on the piping to be reused. And to minimize traffic of structure and components, of removed components that were interferences, we have to temporarily install 5 temporary platforms at different rooms and elevations. You can see it in the sketch in red. It was a challenging activity as well. Okay, let's move forward. How we solve with a specialized company, Mammoth, the rigging and handling of the steam drums? Well, the main challenge is that we have no overhead crane to handle these components, as mentioned before. So they develop a collar type jacking system that have to walk or be propelled over a skidding system. You can see it in the picture. This collar took the steam drum to the conical part, and also had to allow the cutting machine to work properly. You can see it in the picture in blue, just below the collar. And it was developed a skidding system that allowed the steam drum to move in different directions for temporary storing inside the reactor building. This was developed and custom constructed by Mammoth company with support from NASA and all the engineering. Then, for the rigging and handling of the lower assembly, the one to be replaced, it was a most complicated device because you have to go through different elevations and rooms. So we developed basically a system designed to operate on the rails of the existing overhead crane, capable of hoisting, tilting, and rotating the steam generator cartridges far above the elevation of the crane by using a combination of hydraulic entry legs and hydraulic tilting cylinders. That means we have hydraulic towers device here, walking over a girth, main girth, and a main beam here, a rotating beam below, and a tilting device connected to this assembly. The component have to be taken by the center of the gravity with this kind of a trunnion band, and they had to coexist this trunnion band with a temporary support system for holding the steam generators. Remember that steam generators were supported by the column 15 meters high that had to be cut in advance and supported by this system. So was like someone said, this device was like riding your car on the roof, and you will see later on. Was a very smart solution provided by Mammoth company. And then we have the fitting process by PCI. This was also very complex. Usually, when you build a new plant, you put the big components and then you install all the process piping using the component as a fixed point. In this case, we have to remove the big component and fit it to all the existing process piping, mainly the primary heat process piping. So these have to be made with a precision of 0.8 millimeters. Getting this precision in such a big component required of very stages of metrology. And that means metrology before cutting, metrology after cutting. And then with that metrology, we go to the new components. If we machine the new components, taking into account the previous metrology. After doing that, we have to do metrology of the as left condition of the new components and transfers those metrology to the piping to be reused, and then machine the existing piping. It's a kind of a iteration metrology for fitting the new big components to the existing process piping. It was performed by a laser metrology, and basically it was like driving the port to the ship instead of driving the ship to the port. So this scope was performed by PCI from Westinghouse. Some of the contingencies we faced. When you face a mechanical project like this one, some of them you may know, but basically, in our case, a temporary platform installation was too ambitious. We could not install the 100% of the platforms. Some of the contingencies, of course, at found condition, not as per drawings. This caused very big headaches for some days to us. Don't 100% trust in drawings, mainly if they are old drawings, okay? Also, concrete structures, they didn't have the precisions as per drawings, so we have to modify in the last minute some concrete structures. The mismatch between the steam generator nozzles and existing piping, we have contingencies, and of course the center of the gravity of the old components. An old component with degradation inside, a sludge pile inside, you cannot calculate a precise center of the gravity. In this case, we were prepared because the trunnion band for lifting the new component have a regulation in order to allow a correction. We have to use it. Okay, and these are some of the messages I want to leave to you that actually apply for any kind of project. Okay, not only for mechanical project, but for all type of projects. First one, please be part of it. You cannot live or rely 100% rely on contractors or out of house organizations. You need to be present. Okay, be present. Have presence at the shop when manufacturing. Okay, and because many of the issues you may face during the installation process, you can catch it during the manufacturing process. Also, local construction contractors always require more than expected support from the plant staff. Okay, you know your home better, and you can have better details they can catch in a period of time. So you need to be involved. And also during the QC control, during the execution, don't rely on the QC control from contractors. You need to be part of it. This is a must. And every project all around the world, I have catch operating experience from projects all around the world, and it's always the same. Okay? And again, next one, build a team. You will be working with the expertise manpower and with some manpower that have the expertise. You need to build a team between all contractors, and you will get a synergy, a very positive synergy. Okay. Next one, use the learning curve. When you have someone involved in the manufacturing of these new components, it's important that this person will be the same that will be involved during the installation. This is very important. Don't be a hero. You know, young motivated people, you know, like me in those times, usually have a temptation to do our own. But please, this is very important. You always always need some specific support from specific contractors. Okay, so an indeed worldwide qualified contractor survey will be required for this kind of project, mainly in a first of the kind projects. Okay, so it's very important you be very conscious in this point. Okay, that you need to be able to identify where you need specific support. Take the lead of the team, please. Take the lead of the team. Project management by the utility has shown to be the main tool for optimizing the schedule and managing the contingencies. So again, be part of it. It's part of the be part of it. And for the young of Australian young organization, you will love this, but the young blood is required. This project was not only about moving heavy components, but also moving heavy organizations. Nuclear industry have very heavy organizations from the point of bureaucracy and everything. So young, committed, and motivated technicians and professionals shown to be as important as the senior skilled human resources. So young people need to be involved in this kind of big projects. You know, in the early stages of the Contingencies refurbishment projects, the planned life extension was unfeasible if the steam generator required replacement. But everything is possible with the right economical, technical, and human resources. And when I say right, I say reasonable. You cannot have an infinite budget to do a project because it's not feasible. You have to get the reasonable budget and, of course, the technical and human resources. So these are some of the messages I want to leave to you. Here you can find some project data sheet. You know, you can see here that the QC control points, 5,000. We require more than 1.5 million man-hours for the execution at site. And just to understand the scope implemented for the steam generator replacement, we moved 3,000 tons of devices and structures inside the reactor building. So here I share with you some of the people that work with me this project, and thank you very much for your attention. And again, I want to share with you face to face this conclusion and any question you may have. Now, and before taking any question, I want to share with you, and Julian, I need help from you and put in some videos. So movie time, so you don't get bored with so many slides.
All right.
So I leave with Julian the videos, and then for any question you may have, I will respond anything you need.
Thank you very much, Pablo. We'll just have a look at those videos now, and then we'll get on to questions.
The one that has a number 1 is the first one you have to play. Then you have the 2 and the number 3.
La construcción de la central nuclear Embalse significó una decisión estratégica para el país. Durante sus primeros 30 años de operación, la planta fue ejemplo de eficiencia y seguridad. La construcción se inició en 1974. El 13 de marzo de 1983 se produjo la primera criticidad del reactor y en enero de 1984 comenzó su operación comercial. La planta tiene un reactor CANDU y pertenece al tipo de centrales de tubos de presión. Utiliza uranio natural como combustible y su refrigerante y moderador es el agua pesada. El 31 de diciembre de 2015 concluyó su primer ciclo operativo, en el que generó el equivalente a la energía eléctrica consumida por todo el país durante más de 2 años y medio. Luego de su salida de servicio, la planta inició la tercera fase del proyecto Extensión de Vida, en el que se concretó el proceso de reacondicionamiento que le permitirá operar por un nuevo ciclo de 25 años. El trabajo para el reacondicionamiento de la central fue dividido en 3 fases. Fase 1. La etapa inicial del proyecto comprendió el alcance de las tareas que debían realizarse y la estimación del presupuesto total de la obra. Fase 2. Se fabricaron los principales componentes de reemplazo. Se capacitó al personal para realizar las tareas críticas y se definió la planificación y programación del proyecto. También se construyeron más de 8.000 metros cuadrados de instalaciones auxiliares para almacenamiento de componentes y entrenamiento del personal. Licencia ambiental. En julio de 2016, Nucleoeléctrica Argentina recibió la licencia ambiental por parte de la provincia de Córdoba para el desarrollo del proyecto Extensión de Vida. De esta manera, la central nuclear Embalse estuvo lista para la ejecución de la tercera fase del proyecto. Fase 3. 4 actividades principales marcaron al proyecto. El retubado. El reactor de la central nuclear fue renovado por completo. El retubado consistió en el reemplazo de componentes vitales, como tubos de presión y canales de combustible. El entrenamiento del personal se realizó en paralelo con la ejecución de las tareas. La central nuclear Embalse fue el tercer reactor CANDU 6 en ser retubado a nivel mundial. Nucleoeléctrica Argentina fue responsable por la ejecución de esta tarea, en la que participaron 650 técnicos y especialistas. Recambio de los generadores de vapor. Una de las tareas más desafiantes fue el recambio de los generadores de vapor. Por primera vez en la historia, una central CANDU realizó un recambio de componentes de estas características. El montaje de los nuevos componentes involucró el movimiento de 3.000 toneladas de equipamiento, estructuras y dispositivos dentro del edificio del reactor, además de la planificación de aproximadamente 2.000 actividades. La ingeniería conceptual del reemplazo se hizo conjuntamente entre Nucleoeléctrica Argentina y la empresa holandesa especializada en movimientos Mamoet. La construcción de los nuevos generadores de vapor y de los tubos internos intercambiadores de calor fueron realizados por las empresas nacionales. En la ejecución participaron 500 personas de 4 países, de las cuales el 85% corresponde a mano de obra de empresas argentinas. Aumento de potencia. El reacondicionamiento de la central nuclear no solo permitió que la planta opere por 25 años más, sino que también se logró su repotenciación. Pasó de tener una potencia bruta de 648 megawatts a incrementar su potencia a 683 megawatts, un 6% más que en su primer ciclo de vida. Para lograr la repotenciación, se reemplazaron todos los componentes principales del turbogrupo y se agregaron nuevos precalentadores en el ciclo térmico. Además, se reemplazaron todos los sistemas auxiliares por otros de nueva tecnología. Actualización de la instalación. El proyecto contempló la mejora de todos los sistemas de seguridad de la planta. en cumplimiento con los nuevos requerimientos regulatorios. Para ello, fueron instalados 4 generadores diésel de última generación, que tienen la tarea de mantener en funcionamiento equipos esenciales en caso de emergencia. Los generadores anteriores contaban con una potencia instalada de 2.800 kilowatts cada uno, mientras que los nuevos generan 5.200 kilowatts. Para reforzar aún más la seguridad, se instaló el sistema de suministro de energía de emergencia, que contempló el montaje de 2 generadores diésel de 1.600 kilowatts de potencia cada uno. En este proceso se reemplazaron también computadoras de control de la central por unas que presentan mayor versatilidad. Los profesionales y técnicos que trabajaron en el proyecto adquirieron una experiencia invaluable gracias a la magnitud y complejidad de las tareas técnicas. El esfuerzo que realizaron quienes trabajaron en el reacondicionamiento de la central nuclear Embalse augura la continuidad de esta historia de excelencia.
Okay, thank you.
All right, fantastic. There were some amazing videos, and I'm sure everyone's got some questions after all the amazing work we've seen. So I'd like to open the floor for any questions at all for Pablo.
Hi, Pablo. Thank you for your excellent presentations, and congratulations for the success. It's amazing, the work that you did, all the team in Argentina.
Thank you very much.
Yeah, my question is it's about actually 2 questions, but one is about the internal of the steam generator. You mentioned that you found abrasion on the internals. My question is, did you find corrosion as well, taking into account that the material is carbon steel? The second question, I put both questions in one and then leave to you the answer. It's about, you mentioned that you have to cut manually the primary systems on the order of connections. Did you have problem with contaminations or how?
Okay. First question is that we found erosion. Erosion is one type of corrosion or localized corrosion. We had no issues with general corrosion on carbon steel. We only had this localized effect that unfortunately lead to the replacement of the components. And actually, with the alloyed 800 tubing, we didn't have any issue. The tubing was in very good condition, which is the pressure boundary of the primary heat transport system. But unfortunately, with this carbon steel support, we had this effect that made to replace the steam generators. I don't know if you got well the response with this first question. Okay.
Yeah.
And
we're all nodding.
Yeah, it was localized corrosion, but we didn't have any issue with general corrosion. And with the question about the contamination, it's a very good question, but we took into account all the experience, operating experience from all around the world of handling this, and with also from the specialized contractors that we have, and We used different type of countermeasures, like for example, the first stage of the cutting we did it with the machining tool, and the last part of the cutting we did it with a disc without removing material, pressure disc. And even in the last stage of the cutting, we used shaving foam. Have you got that? It's in order to catch any air pollution.
I don't have it.
Yeah, I need it.
Our mics just died, so if we have any further questions, I'll have to get you to come down to speak into the microphone. Yes, you got a question? Or I can relay them.
I'll ask. By standing at the podium, you can look at the camera too. Thanks, Pablo, for that. My question is probably more generally about the refurbishment and whether you could touch on some of the economics involved. Maybe what was the kind of cost of refurbishment all up compared to the initial install cost, and what does that mean for kind of future operating cycles?
Thanks, Ryan.
Okay. What I can tell of that, thank you for the question, is that the steam generator replacement project was a $300 million project. And the entire refurbishment project is about $2,200 million. At that time, it was only the 30% of the cost of the new nuclear power plant, and also with the possibility to be implemented in 30% of the time.
All good?
Yeah.
Cool.
Yeah.
Thanks for that. Does anyone else have another question? We do. We have a question about the schedule and budget. Were they met? Was the project delivered in time? Were there any issues with the budget?
We had we couldn't meet the original schedule. We have an 8-month delay. Okay, and this is basically what we identified. And the reason for that delay is coming from many sources of the project. One part is the steam generator replacement that had to be fitted in the critical path was planned for 60 days, and it was implemented in 87 days. I'm talking about the part of the replacement, rigging and handling, the replacement itself, the handling of the old and new components. And some other issues are coming from a feeder tube welding, and it's a complex. It deserves a specific presentation.
Of course. Very complex project, inevitably has surprises, I suppose. I have a quick question. You mentioned that the lifting of the bottom half of the steam generator had the slight expectation that the center of mass would be off center. Was there any risk of that center of mass shifting as you twisted the bottom half of the steam generator through its motion into a horizontal position? And how did you evaluate the risk of that movement?
Very good question, Julian. First of all, we dried the equipment, okay? That's the main source of any potential movement. Then in a second level, we had the sludge pile at the bottom that it builds up during the operation, but because of the mechanical properties of this sludge pile, we didn't expect any movement. Okay, and then we have the structure itself, and of course we evaluated the condition because the components were degraded, and again we confirmed that there were no any risk of high dynamic loads during the handling.
Okay. So essentially, trying to remove all the potential sources of shifting prior to moving.
That is a very good question, a very important point in handling of big components.
Mm. Are there any further questions that anyone would like to ask of Pablo? Yeah.
Just a question on the laser mapping. How long did it take them to do that? So they had a 1-month shutdown, but how long did it actually take to
map the building? Okay, Pablo, we've got a question on the laser mapping.
Yes.
We understand you had about a month to do the mapping of the building during a shutdown, but how long did the process of laser mapping all the structures take?
Okay, yes, this was implemented in 2 previous outages, and it took to build the entire model of the building. It took about 2 months because we almost used the entire outage to go through all the rooms, and then it took us about, let's say, 4 months post-processing of the data, because once you have all the data, you need to build the model. You need to connect all the scanning, because you cannot do the entire building at the same time. You have to do through different rooms, and then with post-processing of the data to build the entire model. So it's about 2 months plus 4 months of processing.
That's a lot of work. Great. Well, I think that's possibly all we have time for now. We've run a little bit over time, but again, I'd like to thank you all for coming, and I would like to give a special thanks to Pablo for spending his evening talking to us here all the way from Argentina. So if everyone could please show their thanks to Pablo.
Thank you very much to all of you. I hope I can visit Australia one more time, and I hope that this presentation and this experience help to you to find another source of information, but not only information, but also a source of motivation, mainly for the young guys that are starting in the nuclear industry. So thank you very much.
Thank you very much, Pablo. All right. Well,